Black box testing. Black box testing is also known as behavioral testing, focuses on the functional requirements of the software. That is, black box testing technique enable you to derive sets of input conditions that will fully exercise all functional requirements for a program. Black box testing is not an alternative to white box testing. Rather, it is a complementary approach that is likely to uncover a different class of errors than white box methods. Black box testing attempts to find errors in these type of categories: incorrect or missing functions, interface errors, errors in data structures or external database access, behavior or performance errors, and initialization and termination errors. Unlike white box testing, which is performed early in the testing process, black box testing tends to be applied during later stage of testing. Black box testing purposely ignore control structure because attention is focused on the information domain. Tests are designed to answer the following questions: how is functional validity tested? How are system behavior and performance tested? What classes of input will make good test cases? In addition to these questions, few more questions like: is the system particularly sensitive to certain input values? How are the boundaries of data class isolated? What data rates and data volume can the system tolerate? What effect will specific combination of data have on system operation? Tests are designed to answer these type of questions also. By applying black box testing technique, we derive a set of test cases that satisfy the following criteria. 1. Test cases that can reduce the number of additional test cases that must be designed to achieve reasonable testing. That is, we are trying to minimize the effort and time. Second, test cases that tell us something about the presence or absence of classes of errors, rather than an error associated only with the specific test at hand. So let us learn 4 types of black box testing methods. 1. Graph-based testing methods. 2. Equivalence partitioning. 3. Boundary value analysis. 4. Orthogonal array testing. We will learn in detail about each of these black box testing method now. Graph-based testing methods. The first step in black box testing is to understand the objects that are modeled in software and the relationships that connect these objects. Once this has been accomplished, the next step is to define a series of tests that verify all objects have the expected relationship to one another. Stated in another way, software testing begins by creating a graph of important objects and their relationships, and then devising a series of tests that will cover the graph so that each object and relationship is exercised and errors are uncovered. To accomplish these steps, you begin by creating a graph, a collection of nodes that represent objects, links that represent the relationship between objects, node weight that describe the properties of a node, and link weights that describe some characteristic of a link. The symbolic representation of a graph is shown here. Nodes are represented as circles connected by links that take a number of different forms. A directed link, represented by an arrow, indicates that a relationship moves in only one direction. A bidirectional link, also called a symmetric link, implies that the relationship applies in both directions. Parallel links are used when a number of different relationships are established between graph nodes. As a simple example, consider a portion of a graph for word processing application as shown in the figure, where object 1 is a new file for menu selection, object 2 is document window, and object 3 is document text. In the figure, a menu select on new file generates a document window. The node weight of document window provides a list of the window attributes that are to be expected when the window is generated. The link weight indicates that the window must be generated in less than 1.0 seconds. An undirected link establishes a symmetric relationship between the new file menu selection and document text, and parallel links indicate relationships between document window and document text. In reality, a far more detailed graph would have to be generated as a precursor to test case design. You can then derive test cases by traversing the graph and covering each of the relationship shown. These test cases are designed in an attempt to find errors in any of the relationships. Bezier describes a number of behavioral testing methods that can make use of graphs. 1. Transaction flow modeling. The nodes represent steps in some transaction, and the links represent the logical connection between steps. The data flow diagram that we might have prepared during the analysis or design time can be used to assist in creating the graphs of this type. Finite state modeling. The nodes represent different user observable states of the software, and the links represent the transitions that occur to move from state to state. The state diagram that we might have created during the analysis stage or during the planning stage can be used to assist in creating graphs of this type. Data flow modeling. The nodes are data objects and the links are the transformations that occur to translate one data object into another. Timing modeling. The nodes are program objects and the links are the sequential connections between those objects. Link weights are used to specify the required execution times as the program executes. Equivalence partitioning is a black box testing method that divides the input domain of a program into classes of data from which test cases can be derived. An ideal test case single-handedly uncovers a class of errors for example, incorrect processing of all character data, that might otherwise require many test cases to be executed before the general error is observed. Test case design for equivalence partitioning is based on an evaluation of equivalence classes for an input condition using concepts introduced with graph-based testing methods. If a set of objects can be linked by relationships that are symmetric, transitive, and reflexive, an equivalence class is present. An equivalence class represents a set of valid or invalid states for input conditions. Typically, an input condition is either a specific numeric value, a range of values, a set of related values, or a Boolean condition. Equivalence classes may be defined according to the following guidelines. If an input condition specifies a range, one valid and two invalid equivalence classes are defined. If an input condition requires specific value, one valid and two invalid equivalence classes are defined. If an input condition specifies a member of a set, one valid and one invalid equivalence class are defined. If an input condition is Boolean, one valid and one invalid class are defined. By applying these guidelines for the derivation of equivalence classes, test cases for each input domain data item can be developed and executed. Test cases are selected so that the largest number of attributes of an equivalence class are exercised at once. Boundary value analysis. A greater number of errors occurs at the boundaries of the input domain rather than in the sender. It is for this reason that boundary value analysis (BVA) has been developed as a testing technique. Boundary value analysis leads to a selection of test cases that exercise bounding values. Boundary value analysis is a test case design technique that complements equivalence partitioning. Rather than selecting any element of an equivalence class, boundary value analysis leads to the selection of test cases at the edges of the class. Rather than focusing solely on input conditions, boundary value analysis derives test cases from the output domain as well. Guidelines for boundary value analysis are similar in many respects to those provided for equivalence partitioning. 1. If an input condition specifies a range bounded by values A and B, test cases should be designed with values A and B and just above and just below A and B. 2. If an input condition specifies a number of values, test cases should be developed that exercise the minimum and maximum numbers. Values just above and below minimum and maximum are also tested. 3. Apply guidelines 1 and 2 to output conditions. For example, assume that a temperature versus pressure table is required as output from an engineering analysis program. Test cases should be designed to create an output report that produces the maximum and minimum allowable number of table entries. 4. If internal program data structures have prescribed boundaries, for example, a table has a defined limit of 100 entries, be certain to design a test case to exercise the data structure at its boundary. Most software engineers intuitively perform boundary value analysis to some degree. By applying these guidelines, boundary testing will be more complete, thereby having a higher likelihood for error detection. Orthogonal array testing. The number of input parameters is small, and the values that each of the parameters may take are clearly bounded. On such situations, orthogonal array testing can be applied. When these numbers are very small, for example, 3 input parameters are taking on three discrete values each, it is possible to consider every input permutation. However, as the number of input values grows and the number of discrete values for each data item increases, orthogonal array testing can be applied to problems in which the input domain is relatively small but too large to accommodate exhaustive testing. Orthogonal array testing can be used to reduce the number of combinations and provide maximum coverage with a minimum number of test cases. The orthogonal array testing method is particularly useful in finding errors associated with region faults, an error category associated with faulty logic within a software component. When orthogonal array testing occurs, an L9 orthogonal array of test cases is created. The L9 orthogonal array has a balancing property, that is, test cases represented by black dots in the figure are dispersed uniformly throughout the test domain, as illustrated in the right hand cube in figure. Test coverage across the input domain is more complete. To illustrate the use of L9 orthogonal array, consider the send function for a fax application. 4 parameters P1, P2, P3 and P4 are passed to the send function. Each takes on 3 discrete values. For example, P1 takes on values P1 equal to 1, that is send it now, P1 equal to 2, send it 1 hour later, P1 equal to 3, send it after midnight. P2, P3, P4 would also take on values 1, 2 and 3, signifying other send functions. If a one input item at a time testing strategy were chosen, the following sequence of tests P1, P2, P3, P4 would be specified as 1111, 2111, 3111, 1211, 1311, 1121, 1131, 1112, 1113. Such test cases are useful only when one is certain that these test parameters do not interact. They can detect logic faults when a single parameter value makes the software malfunction. These faults are called single mode faults. So, this method cannot detect any interactions. Thus, its ability to detect faults is limited. Here, the number of tests required if exhaustive testing is conducted is 3 power 4 is equal to 81, which is large but manageable. All faults associated with data item permutation would be found, but the effort required is relatively high. The orthogonal array testing approach enables you to provide good test coverage with far fewer test cases than exhaustive strategy. An L9 orthogonal array for the facts and function is illustrated here in the table as shown here. So here it detects and isolates all single mode faults. It also detects all double fault modes and multi-mode faults. Model based testing (MBT) is another black box testing technique that uses information contained in the requirements model as the basis for the generation of test cases. In many cases, the model-based testing technique uses UML state diagrams, an element of the behavioral model, as the basis for the design of test cases. The model-based testing technique requires 5 steps. So the first step of model-based testing technique is analyze an existing behavioral model for the software. Recall that a behavioral model indicates how software will respond to external events. Second step is traverse the behavioral model and specify the inputs that will force the software to make the transition from state to state. The inputs will trigger events that will cause the transition to occur. Third step, review the behavioral model and note the expected outputs as the software makes the transition from state to state. Recall that each state transition is triggered by an event and that as a consequence of the transition, some function is invoked and outputs are created. Fourth step is execute the test cases. Tests can be executed manually or a test script can be created and executed using a testing tool. And finally, the fifth step is compare actual and expected results and take corrective action as required. MBT helps to uncover errors in software behavior, and as a consequence, it is extremely useful when testing event-driven applications. So, let us discuss now the advantages of black box testing. We have seen different types of black box testing now. Now, when we compare with white box testing or glass box testing, we can say that larger units of code can be effectively tested with black box testing. Then for black box testing, tester need not to know how the programming language is used to implement a particular function. So without the knowledge of the implementation, a tester can test the testing process in black box testing. In white box testing, normally the programmer himself has to do the testing activity, but for black box testing, the tester and programmer can be independent of each other. White box testing normally is done from the programmer's point of view, but we know that the functionality or the product is for the user. So the test can be done from user's point of view when we do this black box testing. So it is an advantage. And this black box testing help to expose any ambiguities or inconsistencies in the specifications. Then before the implementation itself, we can design the test cases soon after the specification is complete for black box testing. Now let us see the disadvantages of black box testing. only a small number of possible inputs can actually be tested. To test every possible input stream would take nearly forever, or it is impossible to test all the input values in black box testing. Then second, without clear and concise specifications, test cases is difficult to design for black box testing. Third disadvantage, there may be unnecessary repetition of test inputs. If the tester is not informed of test cases the programmer has already tried.